Opioids encompass a variety of different drugs. These include the illegal drug heroin, as well as clinically prescribed medications like morphine, oxycodone, and codeine. Opioid prescriptions are among the most effective medications for relieving pain. However, their positive analgesic and euphoric attributes are accompanied by a slew of adverse effects, including nausea, respiratory depression, constipation, and a high risk of addiction, a particular area of concern today. According to the CDC, the number of deaths from opioid overdoses in 2017 was 6 times higher than it was in 1999. Additionally, an average of 130 Americans die each day due to an opioid overdose. These facts make determining the mechanisms behind opioid tolerance and addiction, as well as developing alternative medications that avoid these negative effects, an invaluable area of research being conducted today. Opioids target a family of 4 opioid receptors, each of which is responsible for different pharmacological effects. The 4 types of opioid receptors are classified as mu, delta, kappa, and nociception. The receptor responsible for mediating pain relief is the mu-opioid receptor, a type of G-protein coupled receptor. Stimulation of this receptor leads to an analgesic activity that occurs through the activation of its heterotrimeric G-protein. Different ligand agonists and antagonists of the mu-opioid receptor have different effects upon binding, including triggering different conformational changes in the receptor. This is due to the properties of the ligand and the differential nature and activation of GPCRs. However, there are still some common characteristics to this differential signal. The individual steps of agonist and mechanism will be outlined in the following diagrams. First, a ligand such as damgo, an analog of enkephalin, stimulates a mu-opioid receptor by binding to it in its active site. The mu-opioid receptor couples to a G-protein. Recruitment of beta-arrestin protein stimulates the association of dynamin and clathrin to the surrounding membrane. These proteins are elements of the endocytic machinery that forms an endosome containing the phosphorylated mu-opioid receptor. The endocytose receptor will then follow one of 2 pathways: resensitization by dephosphorylation or lysosomal fusion and degradation. Other types of ligands can bind to a mu-opioid receptor without triggering endocytosis. For example, when morphine binds to its receptor, it triggers phosphorylation by protein kinase C instead of by GRK, and the phosphorylated receptor remains on the cell surface. However, when treated with a PKC inhibitor, endocytosis of the mu-opioid receptor will be observed. A number of theories have been proposed to explain the desensitization of mu-opioid receptors and the development of tolerance in response to agonist binding. One theory states that low-efficacy agonists like morphine induce tolerance to a greater extent than high-efficacy agonists. This is due to their reduced ability to stimulate the induction of receptors for resensitization. Another theory describes how morphine leads to little desensitization of mu-opioid receptors, while prolonged signaling from the activated receptor leads to neuronal adaptations that contribute to the development of tolerance. The differing abilities of mu-opioid receptor agonists to induce desensitization and the molecular mechanisms by which they do so is also considered in developing tolerance. Hypotheses such as these form the foundation for much of the current investigation into mu-opioid receptors and their binding ligands. Research by Groer et al. Focusing on mu-opioid receptor agonists salvinorin A, and hercinorin, a chemical derivative of the natural plant compound, represents a positive step toward the development of analgesic medications with limited adverse effects. This study revealed that hercinorin binds to mu-opioid receptors with greater affinity than the other opioid receptor types, and does not lead to much phosphorylation of the receptor. Hercinorin is also able to activate mu-opioid receptors without recruiting beta-arrestin proteins to the membrane. As such, this ligand does not cause significant internalization of the receptor. Overexpressing GRK in cells stimulated by morphine actually promotes mu-opioid receptor internalization over morphine's normal PKC pathway, whereas hercanorin is unaffected by increased GRK concentrations and still does not induce receptor internalization. The current risk of opioid addiction combined with the present opioid crisis makes research on the effects and characteristics of ligand binding to mu-opioid receptors critical. Ultimately, the development of new drugs that can activate the receptor and G protein without leading to desensitization and tolerance will allow for a safe and effective treatment for pain.